Hello everybody! In the last video, we talked about a new vector operation called the dot product. In this video, we're going to see another way the dot product proves to be useful by performing a new kind of calculation called a projection. A projection shows how much one vector points along the direction of another vector. For example, in this diagram here, the vector v lies somewhat above this vector d. The projection of v onto d is this vector right here, this vector called p, and that's called the projection of v onto d. And sometimes we write it with this notation. Vector p is equal to the projection of v onto d. So the vector d is kind of like a subscript here. Sometimes I like to think of this as a shadow vector. That is, if the direction represented the ground, and assume the sun was shining straight down perpendicular to the ground, the projection of v would be the shadow of v cast onto the ground. One important thing is that this shadow happens when the sun is projecting onto a right angle on this vector. Now, projections can be calculated from all sorts of orientations. In these pictures down here, we show a couple of other ways that projections could occur. For instance, here's a vector v and a direction vector d. The projection of the vector v onto d would be this small vector p right here. And again, think of dropping a perpendicular line from the terminal point of v down onto d. And that segment right there represents the vector p. Now it might happen that the direction d, that vector might be shorter than the vector v, but that's all right because d just indicates the direction. It can be extended in either direction as needed. So for example here, to calculate the projection of this vector v onto d, you could imagine extending d and dropping that perpendicular from v, and then this vector would be the projection vector p. For another example, let's say that v is pointing in slightly the opposite direction of d. To draw the projection of v onto d, you'd need to extend d in the opposite direction before you drop that perpendicular line down to draw the projection. And finally, in this example, what if v was perpendicular to d? In that case, if you were to drop a perpendicular line from the terminal point of v down to d, well, you'd actually get the zero vector. Right? No part of v is pointing along the direction of d. It's pointing in a perpendicular direction. So these are some visual examples of projections, but we do want to learn how to calculate these algebraically. And so, we'll break this into two parts. The first part, to calculating the projection, is we'll find the length, how long the projection vector should be. Right? And we'll call that length c. It's sometimes also called the component of the vector v along the direction d. So c is not a vector, c is a number. And then we'll find a unit vector, a vector of length 1, pointing in the same direction as d. Then we could combine these two pieces of information to calculate the projection vector p. That would be that length c times our unit vector. In other words, we're scaling the unit vector by the required length to get the projection vector. When we first started talking about vectors, we also mentioned how vectors can be specified in terms of their length or magnitude and their direction or angle. And these two pieces of data are exactly what we need to calculate the projection vector. So, still, we have the question of how do we calculate this length? One thing you might see once we drop that perpendicular line is we have a right triangle here. And we've recently talked a lot about right triangles. So the way we'll calculate this length c is we'll think about this angle theta, let's call it, between the vector v and the vector d. We'd like to be able to calculate that angle there. The reason being is that one of the trigonometric functions will tell us how to find the length of c. In particular, since side c is adjacent to this angle theta, the function we're going to need is cosine of theta, because cosine theta is defined to be equal to the adjacent side divided by the hypotenuse. In this case, the adjacent side is c, that's what we're looking for, and the hypotenuse is the length of the vector v. Right, so if we know cosine theta, and we're given the vector v, we'll be able to solve for the value of c. Now, as it happens, in the last video, we very conveniently talked about a formula that gives us the cosine of theta. We learned that cosine of theta can be calculated with this formula, v dot d, using that dot product relation, divided by the length of v times the length of d. And so that gives us a way to calculate the cosine of theta. We don't really even need to know the actual angle theta here. We really need its cosine. But if we have that information, if we have one way of writing cosine theta and another way of writing cosine theta, we could combine those equations. We would get c divided by the length of v is equal to v dot d divided by length of v times length of d. You might notice both of these sides of the equation have something in common. In the denominator, we see the length of v on both sides. So we could cancel those out. Imagine multiplying both sides by the length of the vector v, and what we're left with is a nice, not too bad formula to calculate the component, to calculate this length of the projection vector. C will be equal to v dot d divided by the length of d. That's it. So, for an example, let's say we want to find the component of the vector v, 1, 3, onto the vector d, 5, 2. Well, to calculate that, we need v dot d. That's 1 times 5 plus 3 times 2. That's 5 plus 6, that's 11, divided by the length of d. That'll be the square root of 5 squared plus 2 squared. That's the square root of 25 plus 4, or the square root of 29. So the component, this length, is 11 divided by radical 29. As another example, let's say we have the vector v equal to 2, 1, and the vector d equal to 3, negative 2. We want to find that component. Well, v dot d, that's 2 times 3 plus 1 times negative 2. That's 4. The length of d is the square root of 9 plus 4, which is the square root of 13. Right? And that's the length of this line here. It's kind of interesting if v is pointing slightly away from the vector d. So in this example, let's say v is the vector negative 2, 3, and d is the vector 7, 1. In this case, well, as before, c equals v dot d. That's negative 2 times 7 plus 3 times 1. So negative 14 plus 6. That's negative... No, that's not 6. Sorry, negative 2 times 7, that's negative 14 plus 3 times 1, that's 3. Negative 14 plus 3 is negative 11, divided by the length of d, that's the square root of 49 plus 1, the square root of 50. And this time, you'll notice that the component is negative. And that's okay. That just means that this vector is pointing in the opposite direction of the vector d. And that'll also be significant when we calculate the projection. That's how you calculate the component. That's part 1 to getting the projection vector. The second thing we need is a unit vector. We've talked about this in an earlier video, but as a quick review, to calculate a unit vector pointing along the direction of some vector, we generally need to scale it down, and we can do that by dividing a vector by its length. So given a vector d, calculate the length of d, divide d by the length of d, and that will give you your unit vector. And then finally, we need to combine these pieces of information. So we know that the projection vector is c times the vector u, but let's simplify that in the general case to make your life easier. So the component is v dot d divided by the length of d, times the unit vector, that's vector d divided by length of d. So if we expand these out, in the denominators, we actually have the length of d squared. But as we learned previously when we talked about the dot product, the length of a vector squared is the same thing as that vector dotted with itself. And so we can skip the square roots entirely, since this squaring is going to cancel it out. And we can replace length of d squared with d dot d. The numerator, we can't really simplify that too much. That's going to be v dot d. Right? And the dot product gives us regular numbers, so this will give us some kind of fraction that will multiply by the vector d. So this formula, there's a lot of d's in it, but it turns out to be not too difficult to calculate. So let's do a couple of examples of calculating the projection. So these might look familiar. These are the same examples we just saw when we were calculating the component. So we're just taking one more step. A lot of the fractions will probably look familiar. So let's say we have the vector v, that's equal to 1, 3. We want to project that onto the vector d, which is 5, 2. Well, according to our projection formula, we're going to do v dot d in the numerator. So that's 1 times 5 plus 3 times 2. Then in the denominator, that will be d dot d. So 5 times 5 plus 2 times 2, and that fraction is 11/50ths. Do you remember when we did the component, that was 11 divided by radical 50? But remember, we're squaring the length of d here, so that's our fraction, and we have to multiply that by the vector d, so we're going along the direction of d. So 11/50ths times the vector 5, 2. So you can multiply that through, it distributes to each part. And if you want, you absolutely don't have to, but if you like, you can also simplify the fractions. Right? If you're going to use this vector in another calculation, it might be a good idea to simplify. But if this is all we need, we can also leave it in the original form. As a second example, let's say we have the vector v, that's the vector 2, 1, projected onto the vector d, which is the vector 3, -2. In that case, along the top, we have v dot d. Oh, the lights flashed out for a second there. The vector calculation that we need to do, on the numerator, we're going to do v dot d. So that's 2 times 3 plus 1 times -2. That gives us 4. On the bottom, we'll calculate d dot d. That's 3 times 3 plus -2 times -2 is going to be 13. And there's our fraction, and multiply it by the direction d. That's 3, -2. When you multiply that out, the projection vector is 12/13, -8/13. Right, in this case, it's not exactly a to-scale diagram, but it's kind of close. We go to the right, and we're going down a little bit in this case. That makes sense because the vector d is also pointing downish. Finally, let's do this calculation. Let's project the vector v, -2, 3, onto the vector d, 7, 1. And in this case, we're going to expect this fraction to be negative because the vector v is pointing slightly in a different direction than the vector d. So the numerator of the fraction is going to be v dot d. That will be -2 times 7 plus 3 times 1. That's -11. The denominator is d dot d. So 7 times 7 plus 1 times 1, that's 50, times the direction vector d, 7, 1. And if you multiply that through, the vector you'll get is -77/50 and -11/50. So we're going to the left and down a bit. And that's it. That's how you can calculate the projection of one vector onto another. When we start doing calculations with lines and planes in 2 and 3 dimensional space, the projection is going to come in really handy. But that's about it for this calculation. Thanks for watching, and I'll see you in the next video.